Welcome to Lesson 2.4, Good Definitions. So, a few lessons ago, there was a mention of a lawsuit, Procter & Gamble, I believe, with many different companies, and in which the definition of dual-textured cookies ended up being the foundation or the deciding factor for the settlement of $125 million. Now, yes, that is an extreme example of how important definitions can be, but it's also an accurate representation of definitions' importance in the real world. Now, today we are going to look more at the importance mathematically of good definitions. So, the big idea for today can be summarized into the fact that good definitions are clear, accurate, short, and contain only undefined terms or previous definitions. So, those are kind of the 5 pieces or the 5 parts to good definitions mathematically. Number 1, they are clear. 2, they are accurate. 3, they are short, meaning they're not longer than they have to be. And 4, that they contain only undefined terms, or 5 being previous definitions. So containing undefined terms or containing previous definitions are really the only phrasing that our definitions should contain, other than letters and words necessary to create complete sentences. So that's the foundation for our lesson. And then there are 3 properties that good definitions satisfy. So the 3 properties are, 1 being, it uses only words either commonly understood, defined earlier, or purposely undefined, such as points, lines, and planes. Then the second property is that it is accurately describing what is being defined. So obviously, using words that are understood, earlier defined, or purposely undefined is important but meaningless if they are not accurate descriptions of what is being defined. And then our third property is that a good definition includes no more information than what is necessary. So sometimes what I always used to call it when teaching language arts and writing aspects or short responses, extra terminology, extra phrasing, I call fluff. In definitions, we don't want any fluff or extra words, extra padding in our actual definition. We want it to be as short, concise, yet accurate as needed. So then the midpoint. The midpoint of segment AB is the point M on segment AB, with the distance AM being equal to the distance MB. That would be our definition of a midpoint. So in this case, this definition here is what is our accepted definition of a midpoint. So again, the midpoint of a segment, in this case, represented by segment AB, is the point M on segment AB with AM, the distance A to M, being equal to the distance M to B. So in other words, that tells me point M is on segment AB, and it splits AB into two equal parts because AM equals MB. So that would be considered a good definition of a midpoint. Now, example 1 is asking, why are each of these not good definitions of midpoints? So example 1a says the midpoint of segment AB is the point between A and B. And in that case, when we are saying it's not a good definition, we would state which property it goes against. And it might be more than one property in some cases, but we're just going to look at the main property it's violating. So in this case, that statement would violate, or that definition would violate property 2. Property 2 being accurately describing what is defined. It doesn't fully describe what we need to know because the midpoint being any point between A and B could be any point along segment AB. It doesn't tell us that it's going to be right in the middle, splitting it into two halves. So then example B says the midpoint is the ideal location to minimize commuting to A and B. So in this case, we would say that violates property 1. It uses many terms that are not defined or commonly understood. So the midpoint is the ideal. Well, what does ideal mean? We don't know yet. It's not previously defined or defined for us. So the ideal location to minimize commuting. Again, commuting is a pretty broad term, especially for mathematics. So it's using terms that are not commonly understood or earlier defined. And then part C, the midpoint of segment AB is a point on segment AB that makes AM equal to MB and AB equal to 2AM and AB equal to 2MB. So in this case, that would be a violation of property 3, giving us extra information than what is necessary. This first part, midpoint of AB is the point on AB that makes AM equal to MB. That's good. But then adding in this AB equals 2AM and AB equals 2MB is not necessary for understanding and describing the midpoint. And now we're going to look at the idea of a biconditional. So we've already looked at conditional statements and converses, and now we are going to look at another special type of statement that is a biconditional. So a biconditional is a combination of two conditionals, and we would abbreviate it with this symbol here, which stands for if and only if. So this would read P if and only if Q. So an example here would be we're letting P represent the statement D is between A and B, and Q represent the statement the distance AD plus the distance DB equals the distance AB. So then, if P then Q is the biconditional, so if we're going to write that in words, or I read that wrong, sorry, if and only if would be our statement here. So P if and only if Q. So an original conditional statement would just be if P then Q. Our biconditional is P if and only if Q. So the biconditional in this case would read D is between A and B if and only if AD plus DB equals AB. And this is the geometric definition of the phrase between, or the term between. So in order to be between something, between would be considered D is between points A and B if and only if the distance AD plus the distance DB equals the distance AB. So then what we want to explore is the fact that good definitions can be written as biconditionals. So good definitions tend to be able to be written as biconditionals or if and only if statements. So then we are going to look at, sorry, that was going weird. So then we are going to look at the idea of taking two different conditional statements to make up our biconditional. And a biconditional happens when we are combining two parts of true conditional statements. So we're going to look at the definition of a midpoint, for example. The first conditional statement goes from the defined term to tell you its characteristics. So that first conditional statement is telling us the characteristics. So if M is the midpoint of segment AB, then M is on AB and AM equals MB. So that part is telling us the characteristics of the midpoint. The second conditional starts with the characteristics that allow you to use the defined term So then that piece, so again, the idea that the second conditional starts with the characteristics that allow you to use the defined term. So the first conditional goes from the defined term, starting with the defined term, and ending with the characteristics. So goes from the defined term, continues to tell us the characteristics. So that first conditional again, if M is the midpoint, giving us that defined term, M being the midpoint of AB, then telling us the characteristics. The second conditional is going to start with the characteristics and then move into the defined term. So that would be considered, again, the converse of that first conditional. So if the first conditional goes from the term to the characteristics, the converse goes from the characteristics to the term. So that could be written as if M is on AB, segment AB, and the distance AM equals MB, then M is the midpoint of segment AB. So both of these are true conditional statements. The original up here and the converse here. If the original and the converse, so our original conditional and its converse are true, that is what creates our biconditional. So the biconditional is created when our original conditional statement and its converse are both true. So that can be done then, combining these two to be written as the biconditional. So the definition of a midpoint is written as follows. M is the midpoint of segment AB if and only if M is on segment AB and AM equals MB. So that right there, the biconditional statement, is the, again, accepted definition of a midpoint. So then we can look at the idea of a circle being our final example here. And the definition of a circle is the set of all points in a plane at a certain positive distance, its radius from a certain point, its center. So certain meaning specific. So the set of all points, and we know what sets are, we know what points are, we know what planes are. So the set of all points in a plane at a certain positive distance, its radius. So they're using a term radius, but they're defining it, which it is that certain distance, from a certain point, the center. So within the definition of a circle, they're using the term radius, but they're also defining radius in there so it's acceptable to use. So then example 2, part A is saying write the conditional part of the definition of a circle in the direction of if the terms, then the characteristics. So we're starting with the term, or our defined term, moving into the characteristics. So if the term, then the characteristics. So to start with the term, our term being the definition of a circle, so circle being the term. So if a figure is a circle, then, and we want to use the characteristics. So then it is the set of points in a plane at a certain distance from a certain point. Then part B, write the conditional part of the definition of the circle in the direction of if the characteristics, then the term. So if the characteristics, then the term. So that is also the converse to this original statement. So our converse is flipping the antecedent and the consequent. So if the figure is the set of the points in a plane at a certain distance from a certain point, then that figure is a circle. Now, both of those are true individual conditional statements. So if the original and the converse are true, we can write that as a biconditional. So our biconditional would read, a figure is a circle if and only if it is the set of all points in a plane at a certain distance away from a certain point. So the key pieces from today's lesson are, again, the idea of good definitions being clear, accurate, short, and containing only defined or purposely undefined terms. Then the 3 different properties to be satisfied for a good definition, 1, 2, and 3 here. And then that idea of biconditionals, which occur when our conditional statement and its converse are both true, and we write it using if and only if phrasing.